Okay, so we have two postulates for relativity, special relativity. First one was that the laws of physics are the same in all inertial frames. Love that. We don't have to change anything. Maxwell's equations are valid wherever we are. Love the premise. And the second postulate was that the speed of light is the same in all inertial frames as well. Love that. It seems to be right. I mean, as we look at it, there seems to be a speed limit in the universe, and no matter how you look at it, the speed of light is the speed of light. So both of these postulates make extreme sense. What could possibly go wrong? Well, we saw that if you're two observers, things might not be simultaneous in one reference frame as opposed to another. That's one thing. Let's consider another idea, time dilation. Consider this. Let's say you are in a train. You have a laser, and there's a mirror fixed to the ceiling. You're going to shoot a laser beam from your flashlight off of the mirror, and it's going to come back to you. It could happen. You are an observer, and you're in a moving train, so you are in a moving reference frame, if you will. O prime is the observer. Laser emits a pulse of light. You're going to observe these two events. The first event is the beam of light leaving your flashlight, going off, reflecting off the mirror, and coming back to you. So the first event is when it's leaving. The second event is when it arrives back at you. So both those events are happening right where you are. Okay. Observer O prime carries a clock. She measures it to measure the time between these two events. We're going to call this time delta t sub p, the proper time, which means it's characteristic in its own frame. In other words, this is the time in the frame where the events are happening. We call it the proper time. She observes the events that occur at the same place. She measures this proper time to be the total distance traveled, which is there and back again, d and d, 2d, and it's going to travel at the speed of light. So the time for these two events, between these two events, will be delta t proper. All right, let's bring in an outside observer. This man's going to look inside the train from a rest frame, which is the earth frame. And we have a technical scientific term for this man. We call him the stalker. No, he's just an outside observer looking at the train from a rest frame, the earth. He observes the mirror and this train moving, and he sees the light beam, and he sees it go, not straight up and down, but the light beam's going to actually travel this bent path here. It's going to travel, reflect off the mirror, and travel to some further distance this way. As the train has moved along, a distance equal to its velocity times the time that he measures, delta t. By the time light from the laser reaches the mirror, and the mirror is moved to the right, and by the time it comes back, the mirror is moved to the right even further. So light must travel further in his reference frame than it does in her reference frame. Here's a look at it. The light beam is traveling in her reference frame. It's simply going up, reflecting out the mirror, and coming down. In his, it's got to play some kind of game of Pong where it goes off, reflects off the mirror, and it comes back down, and it's traveling this greater bent distance here. Pong is my reference to those of you who remember the first advent of computers. So what are our observations? Well, according to that second postulate of relativity, both observers must observe that the speed of light is the speed of light, c. Doesn't matter which reference frame you're in, then both must measure the speed of light to be the same speed, c. Which means that if it travels a greater distance in the rest frame of the Earth, then it must be traveling for a longer time in that reference frame. So the light travels longer in the reference frame of the Earth, so the measured time interval, delta t, in that reference frame is going to be longer than the proper time in the moving reference frame. Well, the distance, d, can be the total distance for the path traveled in her reference frame, c times the proper time, divided by 2. And if we look at this triangle, the train has moved forward in his time equal to the velocity times delta t, divided by 2, at least to that point for that triangle. So if we look at this triangle, it's a right triangle, by the Pythagorean theorem, this distance, v delta t divided by 2 squared, plus this distance d squared, should equal this distance for the light travel in the rest frame of the Earth, c delta t divided by 2 squared. If we get rid of a 1 over 2 squared on all these terms, get rid of that, and we have that c squared minus v squared times his measured time, delta t squared, is equal to c squared times her measured time, delta t proper squared. And then dividing both sides by c squared, we have 1 minus v squared over c squared. Delta t squared is equal to the proper time squared. Or we can write this as the time he measures in the rest frame of the Earth, delta t, is equal to the proper time where the events are taking place, the time she measures, delta t proper, divided by the square root of 1 minus v squared over c squared, v being the speed of the train, the relative velocity between the two frames of reference, and c being the speed of light. Or we can write it like this. Delta t that he measures is equal to gamma times delta t proper, where gamma is this 1 over the square root of 1 minus v squared over c squared. We're going to use this a lot where we're talking about relative frames of reference moving at speeds of v relative to each other. So we're going to come up with this gamma constant quite a lot. So you want to memorize this form of the gamma constant. For most everyday situations you and I experience on an everyday basis, the velocity that happens is small compared to the velocity of light. So gamma is very, very close to 1. But in all sense, if we have any kind of velocity at all, then in the numerator or in the denominator here, we're going to have 1 minus something, square root, which is going to be a number less than 1, and hence gamma is always going to dominate 1. Gamma itself is going to be a number that dominates 1. Never be less than 1. So the observer O in the ground frame of the Earth will measure a longer time than the observer in the train by this factor of gamma. So it's kind of key in comparing these two frames of reference, who actually has the proper time. The person who has a clock where the events are actually taking place has the proper time. The time interval delta tp between two events measured by an observer at rest with respect to the clock has the proper time. The time interval delta t between two events measured by an observer moving with respect to this clock is always longer than delta t proper. What do we mean by the moving observer in this case? Well, if I'm shooting the laser light and that event is taking place right there in front of me, and the laser light comes back and I receive that laser light event right there in front of me, the events are taking place in my reference frame, and I have the clock. I have the proper time. Anything moving with respect to me, in this case the Earth reference frame is moving with respect to me, is going to measure a longer time than I measure in my reference frame at rest with the events that are taking place. Likewise, a moving clock runs slow. It records less time than an identical clock at rest because the second clock is moving with respect to the clock with the proper time. If you are the clock that has the events taking place, you're going to run slower and record less time than a clock that is moving with respect to you. And that's always going to be true. Sorry I'm late, but you know how time slows down when you speed up. Might be a good excuse for the first time you're late to the lab, but after that it's a lot less funny. So your key in dealing with these problems is going to be able to identify the proper time. The proper time interval, delta t proper, is the proper time. Is the time interval between two events measured by the observer who sees those events occur at the same position in space. Sees them occur right there in front of them. So the clock is there with the events. So your problem-solving challenge, you must be able to identify the observer who measures the proper time and then the observer who doesn't. But your key is always whoever's got the clock and who's seen the events occur in their reference frame right there has the proper time. Anybody else measuring time is going to measure a longer time by this factor of gamma. Here's an alternate view. The woman's view that the man is really the one moving with the speed v to the left and that his clock is running more slowly than hers, he recording a lesser time than she is just as valid as the man's view that she's moving and recording a lesser time than him. The principle of relativity requires that the views of the two observers in uniform relative motion must be equally valid and capable of being checked experimentally. So if they both go by each other and go on in their respective directions forever and ever, each one will conclude that the other person has a lesser time than they do, and they both would be correct. The only problem is when one of them decides to turn around and compare notes. When that happens, then we have a different situation. We have to deal with that situation. And we will look at that situation in just a moment when we look at the twin paradox. But if they continue on their merry way, never turn around to compare notes, then they each conclude that the other person is measuring less time than they are. Time dilation. All physical processes slow down relative to a clock when those processes occur in a frame moving with respect to the clock. These processes can be chemical, biological, as well as physical. Time dilation is a very real phenomena that has been verified by many experiments, and we're going to look at one example right here in a moment. But this has been verified by many data points, has never been shown to be proven wrong. If you prove a theory in science to be wrong, you got to throw it out or modify the theory to accept your exception. Accept your exception. I like that. Because there is no theory that exists that is proven wrong already, because then you throw it out and it doesn't exist anymore. So this theory of relativity is still around, and it's being supported by many data points, and no data points as of yet prove it wrong, so that it has to be thrown out. Here is a real-life example, muon decays. Muons are particles, they're unstable particles. They're created in the upper atmosphere of the Earth by the sun's rays bearing down on atmospheric particles in the upper atmosphere. They have the same charge as an electron, but 207 times more mass than an electron. They have a half-life in the laboratory frame in the proper time of 2.2 microseconds when measured in a reference frame. So if you were to create muons in the laboratory, they would live for 2.2 microseconds before they decay into something else. And that would be the proper time in the rest frame of the muon. Muons travel fast, on the order of 0.991 c, the speed of light. If this time were applied to the Earth frame of reference, the muons should decay before they ever got to Earth. In other words, if they're being created up there in the upper atmosphere of the Earth, and they're traveling at 0.991 c, 991 the speed of light, and they only live for 2.2 microseconds, they only travel about 600 meters before they decay, and they would never make it to the surface of the Earth. However, it's an experimental fact that they are actually being observed on the Earth. So they are surviving to the Earth's location. How is this possible? Well, our gamma in this case at 0.991 c is going to be 1 over the square root of 1 minus 0.991 squared, which is 7.5. So we have a gamma of 7.5, which means on Earth we have a dilated time. Our dilated time in the Earth, which is not the proper time, it is in the rest frame of the Earth, is in fact moving with respect to the proper time, is equal to gamma times the proper time. 7.5 times 2.2 microseconds is 16.5 microseconds. So in our reference frame, the muon is going to survive for much longer than its rest frame survival rate of 2.2 microseconds. It's going to survive for 16.5 microseconds. This would be a distance of 0.991 times the speed of light, 3 times 10 to the 8, times 16.5 microseconds, 4,900 meters, or 4.9 kilometers. So if they're produced in the atmosphere, they will survive for nearly 5 kilometers before they make it down to Earth, and hence can be detected on the Earth. The experiments have measured lifetimes in perfect agreement with the predictions of special relativity. How about that? The twin paradox. Here's a thought experiment involving a set of twins, Speedo and Go Slow. Speedo travels to Sirius. Sirius is the nearest, brightest star to us. I mean, Alpha Centauri is closer, but Sirius is the brightest star in the northern sky. And hence, it's bright because it's close to us. It's only 20 light years away. Only. That's the distance that light would take to get there in 20 years. So 20 years traveling at the speed of light, you get to the Sirius star, and then 20 years to come back at the speed of light. So in other words, if you look outside at night, find the brightest star in the sky, and you find Sirius, the dog star, in your sky, that light you're looking at is already 20 years old, because it's taken 20 years for it to travel from Sirius to you. All right, it's 20 light years away. You're going to travel, you're going to be Speedo, and you're going to travel to Sirius at the speed of 0.95 the speed of light. After reaching Sirius, Speedo immediately turns around and comes back, traveling at the same speed, 0.95 c. When Speedo returns, he is only aged 13 years, but Go Slow, who has stayed on Earth at rest, has aged 42 years. How can this possibly be? How can you be an astronaut, travel around, come back, and there be an age difference between the two twins? Not only that, Sirius is 20 light years away. It takes light 20 years to get there, 20 years to come back. It would take light to travel that distance 40 years. How is it possible that you can go there and back again and only age 13 years when it is, in fact, a total distance of 40 light years? We're going to talk about this. To test this out, though, we need some twins to test the paradox. So we asked around, we looked for some twins. We asked Mary Kay and Ashley, and they would be perfect for this because, normally they'd be perfect for this, but they're making billions of dollars with their time, with their clothing line and et cetera. So they really couldn't afford the time, so to speak, even if it's a shorter time. So they were out. Looked around. We found twins. We found Arnold Schwarzenegger and Danny DeVito. They're twins, at least in the movie, but not biological. So we really needed biological twins. Let's choose. How about Einstein and his long-lost brother, Frank Einstein? Frank Einstein. So we have these two brothers, Einstein and Frank Einstein, and Frank's going to travel away to Sirius, and Einstein's going to stay home. So Frank goes off to the distant star. Einstein stays home, and over that time, years pass. 42 years pass, and he ages. And then Frank Einstein comes back, and he's looking almost as dapper as ever. How is that possible? Well, here's part of the paradox. Which twin is really the traveler? Relativity applies to reference frames moving at relative speeds to one another, uniform speeds. The trip in this thought experiment is not necessarily totally symmetrical, since Frank, Speedo, must experience a series of accelerations during his journey. He's not in what we call an inertial frame. He's going to have to, when he gets to Sirius, he's going to have to turn around and come back, and that's going to require a lot of acceleration to do that. Therefore, we can only be sure of what go slow is measuring. And go slow is not taking the proper time, because the proper time of the events is happening where Frank is. Frank's taking off with the clock, and he's going to arrive at Sirius with the clock. So the events that are key in this problem are occurring with Frank, and he has the proper time. So go slow must be the one who is measuring the longer time. Go slow is measuring 42 years, so we can apply the time dilation formula from his perspective. Assuming that the proper time of 13 years is kept by the twin Speedo or Frank, the key events happen in that frame, even though his frame is not the inertial one. Our gamma in this case is 1 over 1 minus 0.95 squared, square root, which is 3.2. So that's our gamma. Go slow Einstein will measure a time of gamma times the time measured by the proper time. If it takes Frank 13 years to do the journey there and back again, go slow will measure 3.2 times 13, or 42 years. All right. Well, how can we say that Frank only measures 13 years? Good question. We will answer this part of the paradox after we introduce one more idea, and that is length contraction. The measured distance between 2 points depends on the frame of reference of the observer. The proper length, L sub p, of an object is the length of an object measured by someone who is at rest with respect to the object. The length of an object measured in a reference frame that is moving with respect to the object is always less than the proper length. This effect is known as length contraction. How might this be considered? If I have this meter stick in front of me and I measure its length while it's in my hand and it can't go anywhere, I measure it to be 1 meter in length, and that's fine. It's in my reference frame which I'm at rest. That is the proper length of this meter stick, 1 meter. But if it were to move past me with some velocity, I will measure its length to be shorter than what its proper length is. So anything moving past me at some velocity v will be perceived by me to be shorter than what its proper length is. It is going to be length contracted. Here's an illustration. So anything traveling past you, depending on its speed, is going to look shorter along that direction of its velocity than what its length is in its rest frame of its own rest frame, its proper length. The faster it goes, the more contracted it's going to be. Consider a spacecraft traveling with speed v from one star to another. There are two observers. one at rest on Earth and one with respect to the stars, or one at Earth with respect to the stars, that person's going to measure the proper length because they're at rest between the two locations. And the time to complete that journey from their perspective would be equal to this proper length between the two stars, divided by the velocity of the astronaut. The observer in the spacecraft measures the time for the passage of the two stars from the same position. They're in the spacecraft, they're at one star, they measure that event, they go to the other star, they measure that time of arrival at that event. So they have the proper time. Because of time dilation, the proper time is equal to the other time, delta t, divided by gamma. Because a space traveler reaches the second star in this proper time, he or she would conclude that the distance L between the stars is equal to their velocity times their time. They're moving at some velocity v. Their time is equal to the other time, delta t, divided by gamma. So they actually measure a length as equal to the proper length divided by gamma. Their distance for their journey is measured to be shorter than the distance between those two stars by a rest observer on Earth. How about that? So the space traveler's length will be shortened by gamma. And we remember gamma is always dominating 1. It's always greater than 1. So it's going to be shortened by that factor. So let's return to the twin paradox. Light takes 20 years to travel to Sirius. It is 20 light years distance away. Frank, Speedo, only took 6.5 years to complete that journey. He was traveling at 0.95c. How is this possible? Well, let's review. Because the astronaut is measuring a length of space between Earth and Sirius that is in motion with respect to him, the astronaut, this is categorized as a length contraction problem. In other words, even though he's got the proper time where the events are taking place in his reference frame, looking out the window, he sees the Earth and then he sees Sirius. And that length between those 2 points is moving with respect to him as the spacecraft's moving. So the length between those 2 locations is actually contracted. Recall that our gamma in this problem was equal to 3.2. So that's the gamma we're using here. So Frank's observed contracted length is equal to the proper length between here and Sirius, 20 light years, divided by gamma. That's 20 light years divided by 3.2, or 6.25 light years. Frank only thinks that Sirius is 6.25 light years away from his perspective. It is a contracted length. And the astronaut's time measured by him is that length divided by his speed. 6.25 light years divided by 0.95 the speed of light, which is 0.95 light years per year. Light years cancel out. 6.25 divided by 0.95 is 6.56 years. It takes Frank 6.5 years to go the 6.25 light years distance in his reference frame. Now, that's how he can go there and back again in 13 years. The Earth observer's view is that the proper length is 20 light years. Time to travel this from perspective of the Earth is equal to that distance divided by the speed of the traveler, 20 light years. Relative velocity is still the same from both perspectives, 0.95 c. That's 0.95 light years per year, if you will. And that's going to be 21 years. Sounds great. So from the Earth's perspective, it took Frank 21 years to get to Sirius. Now, if you were on the Earth and you want to observe that event of Frank's arrival at Sirius, you would have to still wait 20 more years for that light of that event to come back to you. So it'd be 21 years for Frank to get there, and then you're waiting to see that event. It takes another 20 years for light to travel that distance. So after 41 years, you would finally see Frank arrive at Sirius. And then 1 year later, after 42 years, Frank would arrive back at Earth. So you would see him arrive after 41 years, and then 1 year later, see him actually arrive back where you are. How is that possible? Well, the light of his arrival at Sirius is traveling at the speed of light, and he's right behind it, traveling at near the speed of light. And so the event arrives back to you, and then he arrives right after that. This is the same time we would get from time dilation, this 21 years. If we took 3.2 times the proper time, 6.56 years, we get 21 years. So time dilation, length contraction go hand in hand. On one, the proper time was kept by the astronaut. On the other, the proper length was kept by the Earth observer. So they're not, the proper is not the same for time and length in the same reference frame, necessarily. So, the astronaut returns. He arrives after 42 years, but he only ages 13 years. And he's actually traveled a distance of 40 light years and only took 13 years to do so. Wow. So if you travel even closer to the speed of light, you could probably travel from here to the other side of the galaxy and do it within a reasonable time, a time within your lifetime, so that you could actually go from here to there, because the length would be contracted. Here's Sirius. Here's Frank's early arrival at Sirius. He's really surprised to get there so early. Surely you can't be serious. I am serious. And don't call me Shirley. Okay, so we're going to look at more examples of time dilation and the Lorentz transformation equations in the next lecture.